Hey everybody. So today I was just looking through some GIFs on the computer and I wanted to share some of them with you because they're really quite funny. So anyways, there's a purpose to these GIFs. They go with the lesson, but take a look at this picture right here. Here it comes. Watch the the poor baby. I shouldn't laugh. That's not very nice. Let's go ahead and take a look at another one here. Let's take a look at another one. Let's see. Right here. Here's a good one. Let's take a look at this one. Oh, where did it go? Right there. What just happened? Oops. I don't think that was meant to happen. All right, and I have one more for you guys here that I thought was, well, I guess it's not really that funny, but let's take a look at it. Oh, I think that's an injured person. I think they're even more injured. So anyways, that is just a little teaser for what we're about to learn today. All right, so today's notes are all about Newton's 3 laws of motion. Our essential question is use Newton's 3 laws to explain how things move. So basically, Newton's laws are all the things that help to explain how things move. By the end of this lesson, you are going to be able to list each of Newton's 3 laws of motion and give an example of each. You will also be able to calculate the amount of force needed to move an object based on its mass. So this is a read-only slide, but who is Isaac Newton? So you may have heard of him before. He's an English physicist, mathematician from the 1600s. You might know him as the person who sat under an apple tree, and when the apple fell on his head, he wanted to figure out why did that happen, and so he came up with the law of gravitation. So anyways, he was one of the most influential scientists of all time, and he's the one that formulated or came up with the idea of all things move because of 3 different fundamental ideas. So Newton's 3 laws of motion. All right, so let's get started with these 3 laws of motion. The first law, Newton's first law, all of these laws have a second name. So the first law, second law, third law, but they also go by another name as well. So Newton's first law of motion is also called the law of inertia. And so the law of inertia basically is all those little videos that I was showing you. You know the baby that was sitting on the sled and then the dog decided to move? Well, the baby was sitting there. So the baby is just sitting still until suddenly the dog moves. Well, the baby's body wants to stay there, and then the sled gets pulled from underneath him. So the body wants to stay there. And so the law of inertia basically is the resistance, right? We talked about resistance. Resistance is the opposing of motion, or the opposing to changing of motion. So inertia is the resistance of any object to change its state of motion. Okay, so something that is standing still, like that baby, wants to stay in its position of staying still, right? Or an object that is already in motion wants to stay in motion. So let's talk about that baby. Each of those were, that baby was staying still, and then the sled got pulled from underneath him. the man on the gurney or the stretcher that was put into the back of the truck is standing still, the stretcher is there with the man on it, and suddenly the truck moves and the man's body has a tendency to want to resist moving, and so the truck moves and the stretcher falls off, right? That's basically what that is. Same thing with this soccer ball. So as soon as somebody kicks the ball is going to have a tendency to want to continue going. In fact, if there were no outside forces, this soccer ball would get kicked up into the air and continue to move forever, 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 forever. But we know that doesn't happen, right? It doesn't happen because there are other forces that are acting on that ball. So as the ball goes up into the air, eventually gravity pulls it back down, right? Or as the ball is rolling on the grass, that grass acts like friction, resisting the ball's tendency to want to move. All right, I have an example here as satellites orbiting the Earth as well. So if my fist was the Earth and a satellite goes around, okay, maybe it's easier if I go like this, the satellite is going to continue in motion of space because there's nothing for it to bump into, right? Except that there is space junk. So yes, if that satellite bumps into some space garbage, that's going to change its direction, maybe bump it off of its trajectory, and it won't stay in its orbit. So an object in motion, such as that satellite, will stay in motion unless acted on by another object. All right. This is still part of the law of inertia. And what it says is that when an object has more mass, it's going to have more inertia. Okay? Therefore, more resistance to motion. If it has more mass, it's going to have more inertia, meaning that if it is a rolling ball, like a bowling ball or a golf ball, the one that is heavier, the one that has more mass, is going to be more difficult to stop. So you can imagine the bowling pins at the far end, right? If I rolled a golf ball down the aisle, I may or may not knock the pins over. The pin might be able to deflect the golf ball and cause the golf ball to move over, whereas the bowling ball that has more mass will have a much harder time stopping. All right. All right, Newton's second law. The second law also has a second name, and that is the law of force and acceleration. So what does this mean? It means that an object will only accelerate. Remember, the true meaning of accelerate is a change in speed or a change in direction. An object will only accelerate if there is an unbalanced force acting on it. Okay. The acceleration, as we denote with the letter A, the acceleration of an object is dependent upon two variables. So an object will accelerate more or less depending on how much force is added to the object. So the amount of net force. The other thing that influences acceleration of an object is how much its mass is. There is a formula for figuring out Newton's law, the second law, and that is force is equal to mass times acceleration. And we have one of these fancy triangles so that we can use it when we're trying to solve any of these equations. I have some more examples here on the next page that will help to make it more obvious to you guys what it means. It says here, the greater the mass of the object being accelerated, the greater the amount of force needed to accelerate it. Now let me show you these pictures and it will become more clear. So let's just say that I have Bob, and Bob works at a warehouse and he has to move all of the packages from one area to another. So here we have Bob pushing the cart. there is one package in it, and it's pretty easy to move this cart, so he can go along at a pretty good speed, right? But maybe his boss says to him, hey, Bob, you're not going fast enough. Come on, look at the time. We got to get going. You got to put in more effort here. We got to get these packages moved faster. If he wants to get increased acceleration, how's he going to do that? In order to increase his speed, he's going to have to put in more force, right? To get more acceleration, he's going to need more force. Let's take a look down here. Now let's say that Bob is, again, moving this one package along, and he's going along at a pretty good speed, and then somebody stops and puts a whole bunch more boxes inside of his cart. Now we have way more mass, and it's a little bit more difficult to maintain that same speed. Okay, if he needs to get the job done because boss is watching, he needs to keep his speed the same, but they just added more mass, so what is he going to have to do? He's going to have to either decelerate or he's going to have to increase his mass so that he can keep his production up so boss doesn't tell him that he's going too slow. Newton's third law. Where did it go? There we go. Newton's third law. This has a name also. This is the law of action-reaction. And what that means is that for every action, there is an equal and opposite reaction, right? So whenever an object exerts a force on a second object, so one object is exerting a force on a second object, that second object is going to put a force back on the first one with an equal and opposite force of the first. So I've got a little setup here for you guys. I've got my disinfectant wipes, okay, and I have a board here. So here's my board, okay. I'm going to place it on top, and I know you can't see the whole thing, but it's placed on top there. And if I was a really good kung fu artist, what I would be able to do is back up and go, hi-ya! Right? Well, I didn't actually want to break my board, so I didn't. I could have if I wanted to. But here's the thing. If I was to put 100 newtons of force, yeah, this board is also, my hand is object number 1, the board is object number 2, and this board is also going to put 100 newtons of force back on my hand, right? So it does hurt. It's not like my hand is stronger and just goes through with no problem. It's going to have that same amount of force back on my hand. All right, so there we go. Another example here is the way a rocket works. So when the rocket counts down, 5, 4, 3, 2, 1, blast off. That force of all of the ignition, all of the fuel being ignited causes a force that pushes down on the ground, but that pushing down on the ground pushes up on it also with an equal amount of force, causing the rocket to go up. Now, we're going to be able to see this in our balloon cars that we are going to make. And speaking of that, you guys are going to have to list in your essay of your balloon cars where are each of Newton's 3 laws of motion. Now, we have the law of inertia will be in your car. A mass and acceleration will be in your car. And you will also see how action-reaction is in your car, and you'll have to write about that. So anyways, this basically wraps up. By the end of this lesson, if you are on target, if you were paying attention, you should be able to list for me each of Newton's 3 laws of motion and give an example of each, and you should be able to calculate the amount of force needed to move an object based on its mass. All right, that's it for today, guys. Thanks for joining.